Okay. Yeah, so believe it or not, the background and the theory behind waves and how waves work is much different than all the other kinematic energy forces, things like that. So I thought today I would introduce some of this, I guess the word is like nomenclature, or the theory behind and what all these words mean about waves and things like that. Because if I didn't, this intro video would be like an hour, which is it's just there's so much to understand about waves. So I thought today, because believe it or not, this equation that they kind of just throw at you comes from the fact that these springs, when I turn the air on and the springs go back and forth and the cart, back and forth like that, the behavior of it is actually analogous to what waves do. So ocean waves, next week we'll do a string wave, anything really, and any kind of wave, or as you go on in physics, like energy, the light that's hitting us from these light bulbs is our waves. But as you get into like quantum mechanics, you understand that any like light is waves and particles. Very weird stuff. But anyway, so I thought I would split up the 2 long intros into 2 medium intros instead of making one really easy and one really hard. So let me open a bunch of pictures to explain what these formulas mean. I'll open those when I'm done. The things I wrote on the board were just things that I didn't put in the intro video yesterday, but that a lot of people had questions with. So I thought I'd leave them up there. Okay. The first thing to mention is why this equation, this should really be the first equation. This is what's called Hooke's law. It tells us that the force from a spring, this K determines how strong the spring is a result of stretching the spring away from its equilibrium position. So equilibrium is like x0. That means like once I turn the air on, the string will stretch this way, the string will stretch this way, and the cart will be in a particular position. Every place that you put it away from that particular position, it doesn't like being there. And so that minus sign tells you, I want to go back to that original position. And the reason for that is what they don't really mention in that equation is that all these quantities right here are vectors. So force is not only a quantity, but it's also a vector, and similarly with position. So you can write on a graph sheet, parenthesis x comma y, but that's really a vector that points from the origin to that point. And the rules of like vector subtraction tell me that if a vector is the difference between 2 things, then it points towards the first one. That's not the word subtraction. So if I have a vector A and a vector C, if I want to look at the vector C minus A, it points from A to C. So that's what that means. But for this lab, we can actually ignore that because our setup is on like it's more or less one-dimensional. But the thing that they don't kind of mention in the lab manual, I just wanted to make it explicit whether these are vectors or not. And really, what you can do for all intents and purposes in the lab, instead of, so these are absolute values. This tells me that I can reduce my things from vectors to just numbers. So this is just a force in newtons. It doesn't tell me which direction it is. And the reason I can do this is because of this minus sign. It tells me regardless of whether I push, right? So if x0 is 10 and x is 12 or x is 8, the force is the same because it's pulling me away from the equilibrium position. Everything is defined in terms of the equilibrium position. And so what I did here was I just made a new quantity called delta x. And so that is what you're going to be measuring here. So in your original data sheet, this said position, I think. which I think is a bad name for it. It should really be called delta x, because the thing that actually matters in Hooke's law is the distance from the equilibrium. So if you notice here, what I'm doing is I'm calculating this quantity, my current position and whatever position I initially started at. So for instance, is that a good picture? Not really. So if this is my cart sitting on my air track, and there's a ruler right there, what I'll do before I stretch anything, I'll measure where, let's just say the left edge of my cart. Where does that sit on this? This is actually, you know, it is a meter stick, but those, if you notice, all the numbers are in millimeters because it's like 100, 200, 3. So there are 1,000 millimeters in a meter. So here I'd say, okay, this is 220 or it's more like in the middle. So let's say 650 millimeters right here. If I stretch it over here, actually based on my picture, it looks like I'm using the right edge of my cart, the right edge of the cart. So let's say my cart is initially sitting on the right edge at 6 or 720, and then I pull it over 30 centimeters. So now it'll be like 750. But the actual thing that I'm putting in my data sheet is not either of those numbers, it's the difference between the two of them. So here, the right edge of my cart was at 850 millimeters, and then it was at 943. So I take the difference between the two of those. I'm just converting it to meters because I think it's easier. Okay, that is that. So that's Hooke's law. Now let's get into, yes, I can't do that anymore. That anymore. That anymore. I'll mention that a little bit later. And I'll mention it a little bit. Okay, so now let me talk about where this equation comes from, because it's really not super evident where that comes from. They point you to this section in, I don't know what that textbook stands for, but I found it pretty, well, I didn't look at it, but it's not something that you can just look at and say, oh, okay, that makes sense. So I wanted to run through it really quickly because, believe it or not, it does touch on waves. So what we do is first simplify this equation to just, so instead of delta x, I'm just writing the symbol x. So instead of another way to write this, instead of position that it initially was when you started the lab, like you just press open and opened your blank data sheet, you could write that as displacement. Displacement is how far away from where you started you currently are, which that's an accurate description of it. So if that's displacement, that's what my x is. So F equals negative kx. But I also know there's another expression for F that always holds, is Newton's law. F equals ma. And remember, by the relationship between position, velocity, and acceleration, all I need to do to get from one to the other is to take a bunch of derivatives. So if the position is they write it as r instead of x, whatever. Velocity is the time derivative of that, and acceleration is 2 time derivatives of the position, or displacement in that case. And so what I'm doing is I'm rewriting acceleration as the second derivative of x and equating those two forces, because in equilibrium, they'll equal each other. And I'm going to assume there's no friction in the problem. So I'm writing out this form for F, and I'm writing out this form for F. This step down here is just for convenience. It's a little bit easier to think about if you have something kind of on its own and some coefficient with the next thing. So if I read this out, like if I read this math in English, it is the second derivative of some function x. So I call f or x a function because it has some time dependence. So that's why I'm writing it like x parenthesis t, because at time equals 0, it's at the equilibrium position. At time equal 1, it's somewhere else. At time equal 2, it's somewhere else. So it's a function that, dependent on what time it is, it has a different value. So if I say this in English, the second derivative with respect to time of some function is equal to some negative, some number, and the function itself. So this is where like a common technique in physics, it's called looking for an Onsots. It's like a guess. So you look at this and you say, yeah, it's like I guess another word for like, I guess hypothesis is more like an experiment, whereas Onsots is more like theoretical. It's a guess as to what this possible function can be based on some things that you know. So if I look at like what type of functions do I know? Trig functions are one of them. And if I remember the property of trig functions and their derivatives, I know that, let's just say that this is kind of a tough one because the x is annoying. Just say that x equals sine of t. Then the derivative of that is cos. And then if I take another derivative of it, so now this is the function, and I take a derivative of it, I have a minus sign and exactly the function I started with. So let's just assume that x has the form of some trig function. So where this omega right here is going to tell me how fast my function is oscillating. So for instance, if I went over here and I wanted to show you what that angular frequency, that thing I'm defining right there, which as we'll see, oops, this is a little bit, just don't look at that yet. I thought I had it like blocked off. Anyway, the angular frequency is exactly the thing that we were looking at in like the centripetal force lab. So let me just plot those of, I'll say omega is 50 and cos of omega is 5. And I'll show you what the meaning of omega is. For t equals what we'll see is one of them is oscillating very fast, which means, oh, that's way too much. Let's do 10 and 50. So that we can actually see it. Nope, still too much. Omega is 1 and omega is 10. There we go. So one of them, the omega is 1, is going up and down. The other one is going rapidly. So the one that's going rapidly has a faster angular acceleration, angular frequency, and that means it's just oscillating faster. So it's changing every time. So it's like every 1 second of time, that multiplies it. So it's like if it were just a regular t, it would just be a regular cosine function. But this kind of speeds it up or slows it down if it's less than 1. So based on those rules we were looking at on Google a second ago, I know that the derivative of the cos, this actually comes out with something called chain rule derivative. Which tells me that if I have, maybe make it more explicit. No. So what they're saying here is that their whole function is actually like x squared, but then inside they have another function. This is a very complicated example, actually. Let me just go back to the regular thing. It tells me that if there's some function like this, what I do first is treat the whole thing as if it's some random, like just x to the n. So this would be how I would treat x to the n. I would bring the n down and I would minus that, but then I take the derivative of what's in the inside, like that. So another way to see this, like f would be our, let me compare it here. F, let's just take one. So F would be cosine here, and G of X would be omega of t. So the time derivative of omega of t is just omega. You just take away one of the times. And the derivative of the cos as the whole function is negative sine. Then I'm going to do it again because I know that what I want is to do it twice with respect to time. And so I have the time derivative of the result, negative omega sine omega t. I take that out and I do what's inside. I know that there's no sign change when I go from sine to cos for this derivative, whereas there was with this one. And then here, those two come out, so it's negative omega squared and cos omega t. Now I notice that this is exactly the same x that I plugged in the middle. So I have that two derivatives of the function is equal to negative omega squared and the function itself. So if I compare that to what I had on the last page, I can make the identification that this frequency, the angular frequency squared. So if I compare this equation and this equation, that must be the case. Omega squared is equal to this quantity right here, k over m. Then this is kind of one of the most important equations of harmonic oscillators, which is what we're working with today, this simple harmonic motion. This tells me that the frequency with which the oscillator moves around is determined by the mass of the thing moving around and the spring. So how strong the spring is and how big the mass is. Then right here, I'm substituting the definition of omega that we used in centripetal force lab. Omega is 2 pi times the linear frequency. And then as the last step, I used the definition of period, which was 1 over the frequency. I can reverse this to say frequency is 1 over the period. So that's what I'm plugging in right here. And then in order to flip this equation for t, I just flip this to the top, I flip that to the top, and I flip that to the top. So that is where they get that equation. And one thing I want to point out is that this t, so that t in that equation, that is period, that is not tension. Tension, this is just the hanging mass that hangs over the edge of your device and gravity. So that's just the downward pulling force. Okay, I think, so that is that part. The only other aspect of things is this annoying 1/3. I found it, this factor of 1/3 that you see here, it's an okay explanation. It's this thing called the effective mass, and it basically, a way I can tell you it in English instead of reading this whole and looking at that derivation, which is too much, is that not only does the cart have mass, and so if the cart is moving, it has kinetic energy. The springs are not massless. And, you know, in the lab, you'll see you can either write out the number. It's like they weigh like 9.7 grams or something, or you can weigh them yourself. But they are not 0. And so when they move, they also have kinetic energy. But because the whole thing isn't moving, like basically that part isn't really moving very much, whereas this part is moving a lot. And so it's kind of if you've heard of the concept of like moment of inertia or like the center of mass, it relates to that and doing an integral. Another way, I'll link this in the discussion question. I thought this was a much easier. It's basically an explanation in English of this Wikipedia article, using what I think is a much easier easier way to understand it. Okay, let's head back there. And this is basically just, so in previous labs, this symbol was PE, but this is kinetic energy. Another way, another symbol, you know, other symbols people use, kinetic energy is like, you know, in previous labs, we were looking at what, KE. Other people use T. Yeah, common symbols are KE or T, and then potential energy are U or PE or something like that. sometimes V, yeah. So V, U, or PE, if you see any of those in your test or whatever, those are all potential energies. So this, much like this equation, this is just the relationship between energy and force. We know that like a force and a distance go together in that way. And integrating things, you can tell that if you integrate a force, force energy, basically that U equals 1/2 kx squared is the energy equivalent of the same equation for Hooke's law. So this is the force definition of Hooke's law, and this is the energy definition of Hooke's law. Yeah, so if work or this work energy is the integral of force and displacement, all that you need to do is look at the derivative of this thing. So the derivative of this, you would take the 2 down, that would become a 2, the k would stay, and the x would stay. And the only thing you need to realize is that this negative sign comes up in the force. So for instance, if I look up Hooke's law, the first thing that will come up is totally the force. That's the more common version. But in that Wikipedia article, there will be the energy formula of it. So. Right. Okay, let's see, what else do we need to look at? This is just an example of how to hang your masses on the cart when you start doing like part 2 and 3 and stuff, or I guess with part 2. Part 1 is like hanging a mass over the spring pulley and watching how your cart moves. And this is like part 2 is pulling your cart back, hanging some additional masses on the cart like that. And the only reason I hang it here as opposed to like up here or something is that the photo gate might register the mass and might mess things up a little bit. Also, other than just a few lab stations, I think of one or two of them yesterday had things differently. But if you'll notice, there's a difference here with what this data looks like. You could ignore the velocities. I don't know why that's there in this lab. But if you remember from like our, more or less every single lab we've been doing, with the photo gates, it tells us the time in and the time out. And in order for us to get the time, we would subtract one and the other. This one actually does it for us. I don't know why it didn't before, but yeah, so this is time out minus time in. That's why you notice there's a missing time, and it just tells us gate time. And so you can ignore this statement right here, unless I think it was like that computer yesterday that was like having it looked like the old things. But yeah, unless you see 2 times, you don't need to subtract them. If it just says gate time, that's your actual time. This is for part 3. Let's see what else. That's that. Right, and in part 3, what I want for the particular discussion question to be, the objective of part 1 and of part 2 is to find a spring constant. So for part 1, you take your tension, it's just like your force here. Tension is equal to force. And then you take your displacement, x minus x0 in this column, and you plot those two. So you plot this and you plot this, and using y equals mx, this is your slope. And from this one, let me pull up what we're doing for that. That is taking this period equation and plotting t squared and on the y and m on the x. The way I get that is I square this side of the equation and I square this side of the equation. So I have 2 pi squared, the 4 gets squared and the pi gets squared. And then I'm just rearranging this to make it a little easier for myself. So this ends up being the slope of our equation. And we rearrange that just by dividing on both sides by k and a. So this is slope. this is what slope equals, and you use that to find the spring constant for part 2. And so for each part 1 and part 2, you end up finding a spring constant for one and a spring constant for the other. The thing I want you to do in part 3 is notice that they only give you one place to calculate your potential energy. Just take that cell, Command C and Command V down here, and do another one. So here, use the spring constant from part 1, and here use the spring constant from part 2, and see which one of them makes energy more conserved. So this is using 1/2 mv squared, and this is using 1/2 kx squared, like that energy form of Fick's law. So yeah, basically the discussion question is, if they're different, like for instance, for me, part 2, the spring constant that I got from part 2 was much more accurate in the sense that it led to energy being conserved. Whereas for 1, it wasn't as accurate. And the discussion question is basically, why is that? You'll find that in part 1, when you're moving your card around, it gets kind of stuck a little bit. And that was basically what I meant by that. Okay. And then the last thing is just a few things that people are struggling with. Yeah, so the tension is not the period in that first equation in lab. That's not tension. Tension is just the hanging mass and gravity. And also this one uncertainty equation people were struggling with yesterday, which goes here. People were seeing 7 + 8 and they didn't know what that meant. That just means take the first one. So if effective mass is mass of the glider and mass of the spring times 1/3, the first step I do is equation 8, which tells me how to do sums. Like that. Then I notice that I don't have the uncertainty of 1/3 mass of the spring. I just have the uncertainty of the mass of the spring. So I pull out the 1/3 like equation 7 says. So 1/3 is C, but I still have the square. So it's really like 1/9 uncertainty of the mass of the spring squared. That is all. I will let you get started. And of course, feel free to always ask any questions about these crazy formulas that I try to make sense of for you guys, because it was always annoying for me in college when you would just start a lab and have no idea where the equations come from. Yes, so this is basically, oh yeah, that's the Lagerpro thing I said. That was kind of a discussion question like, yeah, lab asks you just for K for part 1, but try for part 2 as well. And if you're like me, K from part 1 will be much less accurate. And why is that? Okay, that is all.